Hello, welcome to my channel. In this video, we're going to be going through a CSEC past paper, paper 1 solution. This past paper, as you can see, is the June 2019 past paper, paper 1. It consists of 60 questions. As usual, as you can see, those are the instructions, but we're just going to get straight into the questions. I'm going to be breaking this past paper video up into about 4 sections. We're going to look at the first 15 questions and then the next 15 and then the next 15. So we're going to break it up about 4 segments to make it easier for you to digest. And generally the questions would have been broken down similar to how the syllabus is broken down. So like the first part of the syllabus would have been questions on like mechanics, where we look at measurement and other stuff, motion and stuff like that. And also then you would move on to heat and thermal energy, questions on that. And then you'll pretty much move on to waves and light, questions on those, electricity and magnetism, and then questions on radioactivity and physics of the atom. So that's how the syllabus is usually broken down. So we're going to just look at the first 15 questions, and then we follow up with a part 2, with the next 15, and so on. So we'll have about 3 different segments. So we'll start here with question 1. So question 1 says, 3.1415926 expressed as 2 significant figures is, so here we are looking at significant figures, and we just need 2 significant figures. Now, significant figures, as we know, we start to count significant figures from the first non-zero digit. So 3 would have been your first significant figure, and then 1 would have been the second one. And so we'd have 2 there, and then to determine whether you round up 1 or you just drop off what is left, you will look at the number that follows 1. And in this case, it's 4. So when it's less than 5, you just simply drop that off. If it was more than 5 or more, then we would just round up to 3.2. So in this case, it's 3.1. So the answer for this one is 3.1. So once again, we count the significant figures from the first non-zero digit, and that's from 3. Then the next one is 1. And then we look at the third digit to see if it's 5 or more, or if it's less than 5. If it's less than 5, we drop that off. If it's 5 or more, we would round up. So in this case, there's no need to round up. So the answer is 3.1. All right, number 2. All right, so question 2, it says, to measure the external diameter of a measuring cylinder most accurately, one should use a what? So you want to measure external diameter of a measuring cylinder. And so we look at the options. Typically, to measure external and internal diameters, you would probably use a pair of vernier calipers. So let's just look at the options here that we have. So we have a meter rule, tape measure, length of string, and there you go, we have a pair of vernier calipers. So in this case, the answer would have been a pair of vernier calipers. So the answer would have been D as in dog. All right, now we move to question 3. Let me just scroll down. All right, so for question 3, it says a 4 kilogram mass is traveling with a constant speed of 5 meters per second. It is brought to rest in 2 seconds. The average force acting on it to bring it to rest is what? And so to determine the force that will be needed to bring it to rest, we can use Newton's second law, which tells us that the force is equivalent to the mass times the acceleration. And so we could just use that. We know what the acceleration is, the change in the velocity over the time. So we could just put that in. So the mass was 4 kilograms. And then we know that the velocity was changing from 5 meters per second, and it was brought to rest. So the final velocity was 0. So the change was pretty much 5. So we can say the whole change is 5. So the change in velocity was 5, and that is divided by the time. And so what we get here is 10 newtons when we work that out. So your answer here is 10 newtons. So again, pretty straightforward. In this case, the answer would have been C as in cat. And yeah, so that would have been the force needed to bring it to rest. All right, we move to question 4. Oh, I should go down, sorry. All right, so question 4, item 4 refers to the following diagram, which shows two forces, X and Y, applied onto an object. And it says, what should be the magnitude and direction of a third force, which will cause the object to remain stationary? All right, so these two forces are going in the direction of right. So X and Y to the right. So the resultant of those two forces that will keep the box in place must be the forces going to the left. So it must be, if it's just one force that we're going to use, which is the resultant, it would have to be going to the left, and it would have to have the same magnitude. So X plus Y going to the left. So that would be the force that will keep the box stationary. All right. So those two parallel forces pushing on the box to the right, they would be added up because they're all acting in the same direction. So for a resultant of those forces, it would be X plus Y to the right. And so any single force to keep the box stationary would have been X plus Y to the left. So that would have been your answer here in this case. So X plus Y to the left, that is B as in boy. All right, we will go to question number 5. Clear screen here. All right, question 5 says, a boy measured the height of a laboratory table with a meter rule. Which of the following is most likely to be correct? So which of the following, and they capitalize most likely to be correct. So a laboratory table is typically, most times it doesn't even reach a meter height. And the fact that they're using a meter rule to measure it, yeah. So again, it will typically be like a little bit less than a meter, or probably a meter in height. That's the typical height for a laboratory table. And so let's just look at the measurements that we have here. So here we have 0.00895 meters. That's really, really tiny. That's like 0.895 centimeters, basically. Yeah, so that's really small to use a meter rule to measure. So we could say no, that wouldn't be correct. And then we look at B, 0.0895. That's again really small. That's like about 8.9 centimeters. that's really short for the height of a laboratory table. And we look at C, 0.895 meters. That seemed to be in line with what would be probably acceptable. So that would be probably about 89.5, roughly 90 centimeters. That kind of makes sense because a laboratory table is probably a little less than a meter in length, which is 100 centimeters. So that would make more sense. And D is saying 8.95 meter. That is way too much. So that's probably taller than my house. So that's way out. So the most likely answer there would have been C as in cat, which is roughly about 90 centimeters or 0.895 meters, roughly about 90 centimeters. So that's the correct answer there. All right. Question number 6. The diagram below, not drawn to scale. Let me just clear this. The diagram below, not drawn to scale, represents two forces, S and T, acting at O, in which of the following is the resultant in the direction OX. So again, we just have to, check to see basically where the resultant would be. So these are vectors and vector additions. So here we have the first one, A, and we're just going to look at these vectors. So these vectors are joined tail to tail. So S is going from O is in the direction of, I could call that northeast. So that's like in a northeast direction. And then T is in the southeast direction. So I could just complete a nice little parallelogram here and get what the resultant would be. So if I do like this and just complete a nice parallelogram there, then my resultant would be smack in the OX direction. So that would be my resultant right there, smack in the OX direction. So I really don't have to go any further than A, because I've seen that this resultant is smack in the OX direction. But just for sake of helping to clarify to you as well, because you might be saying, looking at B and wondering, could not that be also in the OX direction? Let's just try to do the same thing with this one. So we're going to just try to complete a parallelogram here as well. And we will see that this is a little outside of the OX direction. So this is not quite in the OX direction. This is more like smack in the northeast direction. So that resultant would have been there. So we have already found our answer in this case would have been A. So we need not go any further. Once we have found that, we don't even need to look at the other options. We could, but we don't need to in this case. So your answer here would have been A as in apple. The other two really don't qualify. They're really outliers. So we don't need him to look at those. Usually these questions, when they're given, they're like two options that are really out and two options that are kind of really close. So if you can eliminate two of the options, you're like down to two options to choose from. All right, question number 7. It says, when an astronaut is standing on the moon, his mass is 70 kilograms. When he returns to the Earth, his approximate weight will be. So whether he's on the moon or on Earth, his mass remains the same. However, his weight changes depending on where he is. And so, but his mass will remain the same. So on Earth, his mass is still 70 kilograms, and therefore his weight, which is mass times gravity, right, should be 700. So if we take gravity to be 10, then that would be 70 times 10 So if you take gravity as 10 newtons per kilogram, then we'll have 70 times 10, and that's 700. So his weight is 700 newtons. So your answer in this case is 700. So that's D as in dog. All right. We look at question number 8. So question 8 says, let me just clear that screen. So question 8 says, which of the following rates will determine the power of a machine? So which of the following rates determine the power of a machine? Now, power is the rate of change of energy or the rate of change of work, the rate at which work is done. So, so it says, which of the following rates will determine the power of the machine? So the rate of doing work, certainly, because power is the rate at which work is done. And the rate of converting energy, certainly, because power is also the rate at which energy is converted or energy is changed. So that's certainly the rate of change in temperature, not not quite. So that's not the power. Rate of changing temperature is not power. So power is the rate at which work is done or the rate of converting energy. So 1 and 2 is correct in this case. And so we just look through our responses here. We know that 3 is incorrect. So 1 and 2, anyone that says 1 and 2 only, that should be your answer. So your answer in this case should be C as in cat, 1 and 2 only. All right. All right, we then move to question number 9. Which of the following features must be present in a stable, well-designed racing car? All right, so stability has to do with the center of gravity of the object, and pretty much how the mass and so on is spread out over the object and where the center of gravity is positioned on the object. And so sunroof has nothing to do with stability. Long front or short front, not necessarily affecting it that much. Narrow wheelbase. Narrow wheelbase certainly wouldn't give a better center of gravity because you want the base to be broad. So the broader the base is the stabler the object. So you want the base to be broad, and so it's harder for the object to topple over. So narrow wheelbase, no. Low center of gravity, certainly, because the lower the center of gravity, the more stable the object is. And if the center of gravity is high up, if you remember, probably when you were doing looking at stability and different objects, let's say we have this object, if the center of gravity was here, for example, as opposed to up here, how that would affect the stability of the object. So a low center of gravity certainly will help. All right, so this will certainly aid in the stability of the object. All right, so and for the people who love cars and drive fast, these persons always tend to have nice, huge, nice tires that, when the car is on the road, in Jamaica, we'd say the car sit down on the road and, the car can just run and you don't have to worry about it because wheels are so broad and the car is low and it can run. So that helps the stability of the car. All right, we'll clear that part. All All right, number 10. So the time period of a simple pendulum oscillating with a small amplitude depends on the what? So the time period, if you remember when you do your lab of simple pendulum, we were varying the length of the string, and usually we vary the length of the string, and we observe the time period for oscillation. And so, and we see that there's a relationship between the varying of the length and the time period. And also we see that from the formula for the period of the pendulum as well. So the length of the pendulum is what affects, right, the time period. So it is dependent on the length of the pendulum. So that's the key thing that it is dependent on. All right. And as I said before, it's also there in the formula for the period of the pendulum. If you remember the time period of the simple pendulum, 2 pi square root of L over G, which is the length, and G is gravity, acceleration due to gravity. So G is a constant, and we know that 2 pi is a constant. So the only other variable there is the length. So it depends on the length. All right, number 11. Number 11. Pressure in a liquid can be calculated using the formula pressure equal rho GH. Which of the following sets of units will result, sorry, scroll up too far. Which of the following sets of units will result in the SI unit of pressure? So which of the following sets of units will result in the SI unit of pressure? So the units that we want, we know that for this density must be in kilogram per meter cube. So we know that density must be in kilogram per meter cube. So that's what we want. That's one of the units we want. And then for gravity, we know that must be, that could be in either of the units, but based on what is here, we know what we're looking for. So that is in newtons per kilogram, or it could be meters per second squared, but I think what they're looking for here is Newton per kilogram. So that's the unit for gravity. And then of course, height, just a minute, where is that? And then of course, height is in meters. So those are the units. So density, kilogram per meter cube. Gravity, Newton per kilogram, and height, meters. So that seemed like B as in ball. So the answer to that one is B as in ball. All right, we look at number 12. Number 12 says, which of the following, let me just scroll it up a little bit more. Sure, you're seeing it clearly. Number 12, which of the following is the unit of momentum? So which of the following is the unit of momentum? We know that momentum P is equal to the mass times the velocity. And the mass must be in kilograms. And the velocity must be in meters per second. So what we're looking for is kilogram meters per second. And I think we see that here at B as in boy. So the answer to this one is B as in boy, kilogram meters per second. All right, number 13 says, which of the following quantities has the same value as 6 microcoulomb? Which of the following has the same value as 6 microcoulomb? All right, so we know micro. Once you know what micro is, so micro, 6 microcoulomb, micro stands for 10 to the negative 6. So that should be 6 times 10 to the negative 6 coulombs. So the prefix micro is 10 to the negative 6. So your answer is 6 times 10 to the negative 6 coulomb. That's D as in dog. All right, we'll move to question number 14. Which of the following is an SI-based unit? Which of the following is an SI-based unit? We have about 7 of them. And let us look at these ones to see which one fits. So the volt is not a SI unit, that's a derived unit. The ohm is not a base unit, that's a derived unit. The ampere is an SI unit, that's the SI unit for electric current, which is a base quantity. So once we find out, we don't even need to look at coulomb, but coulomb is also a derived unit and not a base unit. All right, so the answer there is C as in cat, ampere. All right, hope you're understanding everything so far. And there is no issues so far. All right, item number 15. Says item number 15 refers to the following graph, which shows how the displacement of a runner from a starting line varies with time. So we have the displacement on the y-axis and time on the x-axis. And we see the graph there. It says from the graph, it can be deducted that the runner is what? The runner is going slower and slower. The runner is going at a steady speed. The runner is going faster and faster. The runner is not moving. From the graph, it may be seen that the runner is going at a steady speed. So if we realize just by estimation in a displacement of 12 meters, it took 50 seconds, sorry. That's approximately about 1/4. That's approximately about 1/4 or 0.25 meters per second approximately. And when it reaches to 24 meters, the time is 100 seconds, which is also approximately a quarter, 0.25 meters per second. So that's pretty steady. So, and also this straight sloping line going up should also tell you that the speed is constant or steady. So the answer for this question is B as in boy. It's going at a steady speed. All right. I will pause this video at number 15 and you pick up in part 2 with number 16 through to 30.